We're going to shift gears a little bit here and talk about motion of planets in the sky. Call it heavenly motion. Now, what does this have to do with what we've been talking about thus far in the unit, circular motion? We're going to find here shortly that most of the objects in the sky follow not quite circular orbits around other things, but almost circular orbits around other things. So it allows us to use some of the analysis that we've already learned in other contexts in the context of the heavens or the skies. We're going to do a little history first, though, just a short history lesson, though, on our current understanding, our current notion of the motion of planets and the motion of stars and so on. Way back, like a long, long time ago, not in a galaxy far, far away, but in our galaxy, we're talking like 2,000 years ago, Greece, so our galaxy, still a long time ago. Aristotle, that's more like 2,500 years ago. A guy named Ptolemy, which was, 100 years after the death of Christ, about 140 AD. Both of them said kind of the same thing, and that is that the Earth is the center of the universe. Everything revolves around the Earth, including the sun. Now, we know that's not the case now, right? At least most of us do. Those of us who still believe the Earth is flat may not know that the Earth is not the center of the universe, but most of us do. Why do we know this, though? Not because we're way smarter than Aristotle or Ptolemy. Why do we know that the Earth is not the center of the universe? Because someone told us, probably. Most of us aren't smart enough to figure that out on our own. How do I know that the Earth is not the center of the universe? Because somebody a long time ago told me that. When I wake up in the morning and I drive to school, the sun is often rising. When I pull into the schoolyard, the sun is rising over there in the east. And then later on in the day, I look outside, oh, the sun's over there in the southeast. And then later on, I look over there, the sun's in the south, and then the southwest, and sets in the west. And if I didn't know better, like I would throughout the day think, oh, the sun is moving around the Earth. That's what it looks like, right? So as much as we know that's not correct, like it's not that far out to think that somebody 2,000 years ago would look up in the sky and say, yeah, the sun revolves around the Earth. Everything else revolves around the Earth too. The Earth must be the center of the universe. So just because it's wrong doesn't mean the people that came up with that theory are not very smart. It's just that we have the benefit of a lot of smart people coming before us that these guys didn't have the benefit of. So, first step, that first stage in the evolution of our current understanding of our solar system and our universe, the geocentric theory. Geo meaning Earth, centric meaning centered, Earth-centered theory. The Earth is the center of the universe, and everything else, all the other planets, all the other stars, everything else revolves around the Earth, which of course we know to be wrong. But isn't so crazy, if you were around 2,000 years ago. So let's zoom forward like a long time. Let's zoom forward to let's say the 16th century. Ever heard this guy's name before, Copernicus?
I did a project on him before. So nobody asked.
Did you? No, I did ask. Copernicus, mid-16th century, turns everything literally upside down. The Earth is not the center of the universe. We don't have the geocentric theory anymore. We have what we call the heliocentric. Helio means sun. The sun-centered theory of the solar system. The sun is the center of our solar system, and all the planets, including the Earth, revolve around the sun. You ever sit in your car, like mom or dad is in at a store, or they're in at 7-Eleven, whatever, and you're nodding off in the car, and then all of a sudden you wake up when the car next to you is backing out, and it feels to you like you're going forward, and you panic just for a second. You ever noticed that? You ever felt that? It's relative motion, right? If it doesn't matter whether the car beside us is going backwards or we're going forwards. It looks on the surface like the same thing. It doesn't matter whether we're revolving around the sun or the sun is revolving around us. It looks like pretty much the same thing, right? But there is a correct answer. The car beside us at 7-Eleven was backing up, even though it looked to us like maybe we were going forward. Well, we know that the Earth revolves around the sun, even though it looks to us like the sun revolves around the Earth. So this is pretty controversial at the time, but like really controversial at the time. But we now, beyond a shadow of a doubt, we now know this to be absolutely correct. The Earth is not the center of the solar system. Rather, the sun is, and the Earth and all the other planets revolve around it. So now it becomes a matter of a little bit of refinement. Like the big revolution has occurred. We've got the Earth revolving around the sun rather than what was previously thought the sun revolves around the Earth. The revolution is over. And now it's just evolution. Now we got the big theory, let's refine the big theory. Let's evolve the big theory so that we learn a little bit more detail of the Earth revolving around the sun. So fast forward maybe 50 years, I'm not sure the exact date, about 50 years, to a guy named Tycho Brahe. Tycho Brahe took some observations. We call them naked eye observations. It doesn't mean he was naked when he made these observations. It means he may have been, I don't know. But we're not going to say that he was because we don't know. He took naked eye observations, which means that he basically looked up into the sky and noticed things, observed things. Where is this planet? Where is this star at this time of day? Where is the sun? Where is the sun setting at this time of year? What about the shadow that the sun casts and whatever? He took all these different naked eye observations. We mean just like observing things without actually measuring things with angles and so on and so on and so on. Took all these naked eye observations with an assistant of his named Johann Kepler. He didn't really do anything with these observations. He just took the observations down, recorded them, and had them in this little journal or this big journal. Then, after he died, his assistant Kepler did some work with them, actually used these observations to develop some theories. Tycho Brahe's assistant, Johann Kepler, took those observations and didn't just show that the Earth revolves around the sun, but actually described the motion, like exactly what that motion looks like. How they move, rather than how they move. That doesn't make sense. How they move, rather than how they move as they do. Let's just say how they move. He described the motion of the planets, like not just this is what's happening, but that they're going around the sun, but rather they're going around the sun this way. It's taken this path. Here's some equations to describe it, and so on. Developed 3 laws. Called them Kepler's 3 laws. They're vastly different from Newton's 3 laws, but just like Newton's 3 laws, we have to go in order. The first law is called the law of elliptical orbits. Now, hold off before you draw this. I'll give you a chance to draw this at the end, okay? I want to explain it first. This diagram, as it's drawn here right now, should not make any sense to you because it has 2 suns. We do not have 2 suns in our solar system. We have 1. But the law of the elliptical orbits says that the Earth and all the other planets, we'll talk about the Earth, but the same thing happens for all the planets. Jupiter, Mars, Neptune. All the planets, including the Earth, revolve around the sun in an elliptical orbit. An ellipse is like a stretched out circle, right? Like almost like an egg shaped. Yeah. Yeah, like a circle is actually a type of ellipse, right? Except that a circle is just a non-stretched ellipse. All the planets travel in an elliptical orbit around the sun. Now, each ellipse, as you draw an ellipse, there's two what we call focal points of the ellipse. One focal point would exist here, and one focal point would exist there. The sun is at one of those focal points. Now, I've got it drawn in two places there. That doesn't mean the sun is at two places. And it doesn't mean that the sun goes back and forth between two places. And it doesn't mean that the sun decides where to go because of the orbit of the Earth. Rather, the sun is where it is. Like, let's say the sun is right here. The path of the Earth would be an elliptical orbit around the sun like this, or the path of the Earth would be an elliptical orbit around the sun like this. So the Earth revolves around the sun in an ellipse, a stretched out circle, such that the sun is at one of the two focal points of that ellipse. Does that make some sense? Sun's not here and here. The sun's here or here, and wherever it is where it stays. Okay, does it make sense? So let me write that out for you, and then you can copy down the picture, copy down whatever you need to copy down, including the words here. We'll say that the path of the Earth around the sun, the path of a planet around the sun, is an ellipse, which is a stretched out circle with the sun at one of the focal points. Two focal points for every ellipse. The sun decides where to go, and then the planet decides where to go in response to where the sun is. Just got to make sure that the sun stays at one of the focal points of that ellipse. Second law. The second law is called the law of equal areas. This diagram is even more confusing when you look at it right now. This will make absolutely no sense until I explain it. Hopefully then it will make some sense. So put your pens down and just listen as I'm explaining this, and then we'll give you a chance to write this down afterwards, just like in the last one. The law of equal areas says this. The Earth, as it revolves around the sun in an elliptical orbit, has an imaginary line that joins it to the sun. The Earth and all the other planets, right? This works for Mars as well as it works for Earth. There's an imaginary line joining the Earth to the sun. It's not like there's a real string there. Okay, there's no rod. There's just this imaginary line that joins the Earth to the sun. Now, if we look at a certain time interval that we'll call T1, a little bit down the road, that time interval, that line that joins the sun to the Earth has swept out a certain area. Now, I don't know how we'd calculate that area because it's a really odd shape, but there is an area that's swept out. If we're good enough mathematically, we could find out how much area that is that's covered by that line as it went from this position to this position over a certain amount of time that we call T1. Does that make sense? So in that amount of time, T1, a certain amount of area has been swept out by that imaginary line. Now, let's fast forward, like whatever, 2 months, 6 months, 8 months, 5 days, whatever, doesn't matter. Okay, we're going to say about 6 months, so that now the Earth is over here. There's still that imaginary line joining the Earth to the sun. If a certain amount of time later, T2, that much time later, we look at where the Earth is, then the line that joins the Earth to the sun has swept out another area that we call A2. Okay, does that make sense? So in this time interval, T1, this line has swept out this area, A1. In this time interval, T2, then this line has swept out this area, A2. But here's the kicker, and here's the really important part of it. If T1 equals T2, In other words, if this is, let's say, 3 days, and this is 3 days, make sense? If those two times are the same, then A1 will equal A2. Then those two areas will be the same as well. The times aren't the same, the areas aren't the same. Times are the same, the areas are the same. Now, like, you could say, well, yeah, sure, that's a neat little mathematical thing, but so what? Those areas swept out are the same if the time intervals are the same. Let's look at the implication of this, right? Because the Earth is closer to the sun here than it is here, in order to make those areas the same, this line has to be longer than this line. In other words, if those two areas are the same in the same amount of time interval, these two times are the same, t1 and t2, then the Earth must change speed. In order to cover this much distance in that amount of time versus this much distance in this amount of time, the Earth and all the other planets must speed up as they get closer to the Earth and then slow down as they get further away, closer to the sun, I should say. The Earth speeds up as it gets closer to the sun, and then it slows down. And then it speeds up, and then it slows down. So, during equal time intervals, T1 and T2 are the same. The area swept out by a line joining the Earth to the sun, the areas are going to be equal. And the implication of that is the speed of all the planets as it goes around the sun changes. The planets speed up as they get closer to the sun, and they slow down as they get further away. Does that make sense? Okay, let me write this out in words. During equal time intervals, so I'll put in brackets here, if T1 equals T2, an imaginary line or a line joining the sun to a planet sweeps out equal areas. In other words, if T1 equals T2, then A1 equals A2. And the implication of that is that planets travel faster as they're closer to the sun. The last of Kepler's laws is called the law of periods. The law of periods says this. Again, just listen to this and I'll give you a chance to write it down in a second here. It says the average period of revolution of a planet around the sun squared is proportional to the cube of the average radius of revolution. Now, that doesn't seem to have any kind of importance or implication whatsoever until we look at it a little bit closer. Let me write that down, though. T squared is related to, you ever seen that symbol? This kind of fish symbol?
Yeah, it's on the back of every Christian, so you know.
Well, yes, but it doesn't mean the same thing there. It means it's related to, it's proportional to. As if x is proportional to y, then as y goes up, x goes up. Does that make sense? If x is proportional to the inverse of y, then as y goes up, x goes down. Okay? So t squared is proportional to r cubed, which means that t squared over r cubed is equal to a number, k, that we're going to call Kepler's constant. And here's what's neat about this. Kepler's constant will be the same for each central body. And what do I mean by central body? Something that's being orbited around. The sun is a central body. The Earth revolves around the central body of the sun. Now, it doesn't matter whether we use data for the Earth revolving around the sun or Mars revolving around the sun. Kepler's constant for the sun is the same. So, for instance, we can say t squared over r cubed for the Earth is equal to Kepler's constant for the sun. So 365 days, the period of the Earth's revolution, squared, divided by the average radius of the Earth's, sorry, that should be r cubed, divided by the average radius of the Earth's revolution around the sun cubed is equal to k. But if we look at t squared over r cubed for Mars, it's also equal to Kepler's constant for the sun. These two numbers are the same. As long as we have the same central body, the same thing being revolved around, then Kepler's constant will be the same, whether we use data for one planet or another. So what? Well, if we know something about the Earth and its orbit around the sun, then we can deduce something about the orbit of another planet. So we know t squared, let's say, we know t and r for the Earth. We calculate k. Now we know k and maybe t for Mars. So we can determine r. So using the properties of one planet, we can deduce the properties of another planet. Does that make sense? Yep. Well, you'd be trying to find r, or t, or whatever, right? The cube and the squared is just the relationship that exists. Now, having said all that, if you're looking at Kepler's constant for another central body, a different central body, like star X, let's say, well, t squared over r cubed for planet A could be equal to Kepler's constant for star X. T squared over r cubed for planet B that revolves around X would be equal to Kepler's constant for X. But Kepler's constant for X is not the same as it is for our sun. So whatever revolves around X produces the same Kepler's constant. Whatever revolves around the sun produces the same Kepler's constant, which allow us to take data from one planet and deduce information about another planet. Okay, write down what you need to write down for that now.